The setting for the Narrows Bridge over the Swan River in Western Australia is one of natural beauty and charm, in which the graceful proportions and simplicity in design of the bridge harmonize with the aesthetics of the site. The project was planned in the 1950s, when rapid development in the Perth metropolitan area foreshadowed the need for an alternative traffic highway over the river. Preliminary investigations indicated the advantage of seeking overseas professional consultation for the direction of the project. Main Roads Department engineers and the consultants worked in close collaboration. As the river at the Narrows has a width of only 700 to 800 feet, the location of a bridge here was a natural choice. Reclamation of a section of the bay on the north side of the proposed bridge constituted a major works project in itself. The dredge Stirling was allocated the task of reclaiming some 60 acres of Perth water. Over a period of 42 months, a total of 1 3/4 million cubic yards of material was dredged. As filling accumulated, displaced water flowed out through a channel. Suction dredging of sand and shell provided the foundations for the northern approaches to the bridge prior to the commencement of building operations. Under the reclaimed area, there is up to 70 feet of mud. The approaches were planned with easy grades for traffic moving on and off the bridge. Another preliminary was the establishment of a yard at the south end for the casting of concrete units required in the construction and the assembly of various components and materials used in the course of construction. Bridge building work commenced from the south end, when timber piles were driven for the temporary staging. A floating plant of the Harbours and Rivers Department was engaged in this operation, using a 2.5-ton hammer to drive the timber piles. Staging work advanced rapidly and soon extended into the stream. More than 100 piles were driven within a month. An access bridge with rail track was built along the downstream side of the temporary staging, and the pile tops were levelled for the erection at a later stage of timber trestling. A pile driving frame and travelling gantry were used. The permanent piles used for the foundation of the piers and abutments are a type known as Gambia piles. Devised by the consultants, this type was first used in Gambia, West Africa, on similar work. The pile casings were made from 3/8 of an inch steel plates and were fabricated at the State Engineering Works. A hydraulic press initiates the curvature to be applied to the steel plates. Then, by passage through rollers, the individual plates are made cylindrical in shape. The two rolled ends almost meet together. Preliminary tacking precedes the joining at the seams, and a cramp is used to hold the joint together. The rolled casing is then ready for complete welding at the seams. Longitudinal welding of the sections follows. This is done by the submerged arc process. On completion of the welding, all slag is removed with a chipping hammer. The short lengths of circular steel casings measure 31 3/4 inches on the outside diameter. The Gambia steel casing, now in 6-foot lengths, will be extended by joining units to make 30-foot lengths before delivery. They are aligned and pinned or tacked preparatory to being welded together. A circumferential weld was made by rotating the pipe to allow welding by submerged arc. The casings or tubes now welded to 30-foot lengths are moved from the workshops to the yard, ready for delivery to the bridge site. In all, 180 piles were used in the construction of the bridge. At Mill Point on the south side, a special yard was used for the preparation of the casings prior to the driving. The lower part of each tube was filled with reinforced concrete for a depth of 15 feet. First, the steel reinforcement with the driving nose attached is drawn into the 31 3/4 inch diameter tube. This first section will take the driving of a 10-ton drop hammer. The blows will be delivered to a removable driving helmet or dolly located above the initial 15 feet of reinforced concrete. The tapered driving toe will then penetrate mud and sand to a solid foundation. After preparation, the driving sections of the casings are racked to receive the pour of concrete. Along the access way, the casings are brought to the required position for building the pier. After driving these tubes to the complete depth, they will be filled with reinforced concrete. The Gambia pile is designed so that reliance is placed only on the concrete core. Thus, corrosion of the outer steel tube is of no consequence. The mobile piling crane holds the tubes in position for a vertical drive and directs the driving hammer inside the casing. The 10-ton drop hammer operates inside the tube, delivering its blows to the driving helmet lying on the concrete above the toe. These casings or tubes are driven through the silts and mud into the underlying sands. Each 30-foot length of tubing is brought to the vertical position and welded to the section already driven. The lengths of the completed Gambia piles vary from 80 feet to 120 feet. When driven, they are founded on very firm sand overlying limestone. Each pile can carry a maximum dead load of 200 tons, increasing to 250 tons with traffic loads. Pile after pile was extended as required by welding on additional 30-foot lengths of tube and driving further into the firm sands. Finally, the top of each pile was trimmed to the required level. Lengths of steel reinforcement, fabricated to correct dimension, are brought to the pier positions. Each length of reinforcement is then lifted by crane into a position for entering the pile casing. After the reinforcement had been adjusted, the casings were filled with concrete and compacted. On the temporary wooden piles driven into the bed of the river between the permanent piers was constructed a forest of jarrah falsework to carry the units or elements which would eventually form the post-tensioned deck structure. The bridge is a pre-stressed concrete structure stressed by post-tensioning. The operation of longitudinally stressing the precast deck elements and uniting them structurally was effected by erecting the 8 lines of beams on falsework with 2 cantilevers, each 370 feet long. 2 suspended end spans and a center span were temporarily erected at a higher level, and after stressing, lowered onto the cantilever seatings. The south span was lowered first, followed by the north suspended span. Here it is shown diagrammatically as one unit, but in fact each span was lowered in 4 groups of 2 beams each. Finally, the 4 groups forming the center span were lowered, and structural continuity was achieved by tensioned cables at the junction of the suspended spans and cantilevers. The shore piers are of simple design in reinforced concrete founded on gambia piles. In the river, precast concrete skirt pieces screen the gambia pile heads. The bridge columns are of reinforced concrete, each supporting 2 deck beams. 4 columns supporting 8 beams are provided at each pier. Anticipated movement in the sand at the north shore necessitated modifications to the gambia piles. To permit this movement without causing a stress in the supporting piles, a different pile casing was used. These casings had an enlarged top section in which precast reinforced concrete piles were placed and bonded into reinforced concrete at the bottom. This upper part of the pile consisted of 60 feet of concrete column placed inside a 48-inch diameter steel shell after driving. The space between the pile and the casing permits deflection with ground movement of the steel shell, which will bend. But any deflection of the steel casing will not be transmitted to the precast concrete column supporting the bridge pier. Thus, all of the piles for the North Shore Pier were constructed in this manner to overcome any possible movement in the reclaimed ground through which they were driven. A special casting yard was constructed on the mill point area for the preparation of the units which would form the deck structure. The bridge was built with short precast units and separate diaphragms. In all, 12,600 cubic yards of Portland cement concrete were used. The quantities of selected sand, metal aggregate and cement were brought to the hoppers and fed by skip in measured supply to the concrete mixer. Mixed concrete was delivered to the casting sections by the monorail method. The superstructure in pre-stressed concrete embraces 8 lines of I-beams. The elements for these were cast in the yard, and to simplify the construction, the beams were detailed so that the bottom flange and lower section of the web were cast first. A few days later, the remainder of the section was cast in a second mould, which was bolted to the lower part of the web. The second mould could thus be of standard shape. The variable depth of the web of each unit was obtained at this stage of casting. The union of the top flanges by in situ concrete was effected after beam tensioning. The beams of the deck structure were made up of these precast units, which were transported on bogies travelling on a narrow gauge truck. From the bogies they were lifted by a travelling Goliath crane and placed in position on a staging or false work formed of jarrah poles driven as piles. After the sections had been placed on the staging and lined to position, they were adjusted to level by small screw jacks, and the 3-inch gap between the sections was filled with concrete. 5 30-inch diameter water mains and 2 15-inch gas mains were slung underneath the bridge deck. Provision was made for high-voltage electricity cables and the PMG telephone lines under the footway slabs. Here can be seen the anchor blocks at the end of a section ready to take the tensioning cables. The purpose of constructing sections of the bridge at a higher level and supporting them on temporary trestling was to provide access for threading and tensioning the cables. When tensioned, the elevated sections will be lowered on jacks until the halved ends engage. And so, from the casting yard, the units were brought in predetermined succession, each fitting into its position and supported temporarily on the forest of falsework. Close limits were set on the structural depths at certain points by the headroom requirements for the underpass roads and motorway levels. At this stage of the construction of the bridge, the south suspended span has been lowered into position. During its construction, the bridge engineers had to provide for a temporary navigational channel to be opened for river traffic. Above this maze of falsework, the Narrows Bridge was gradually taking shape. Heavy steel girders supported the precast elements over the temporary navigation channel. The length of the bridge between the abutments is 1,100 feet, and the carriageway will be 70 feet wide, providing for 6 lanes of traffic. There will be a footway on each side of the bridge. Each footpath will be 8 feet wide, separated from the carriageway by a 2-foot wide safety curb and fence. The headroom for river traffic in the navigation channel will be 26 feet, and for road traffic on the riverside roads, 15 feet. The bridge is on a vertical curve with a 4% approach gradient. To permit longitudinal expansion and contraction to take place with the minimum of frictional resistance, the 4 columns supporting the 8 beams have curved bearing plates, top and bottom, which are in contact with plates on the beams and piers, so that the curved plates form part of a cylindrical surface. And now the tensioning. Tests made on stranded wire ropes led to the development for this structure of a rope of 0.7-inch diameter comprising 19 wires, which is used with a split wedge anchor. Lengths of wire rope were fed along the assembled section. The groups of wire ropes imposing the longitudinal pre-stressing force were placed outside the web. The tensioning force was applied at each end of the rope, and when the required force was reached, it was secured by slip wedge anchor grips. The pre-stressing forces were accurately measured with load cells, the readings being taken on mirror galvanometers. The initial stress in the wires was 83 tons, and the final stress 63 tons per square inch. This is equivalent to 20 tons per rope. Although load cells were used for the final reading, a check on the load was made by measuring the extension of the cable. After tensioning, the cables were surrounded by concrete as protection against corrosion. In addition, the concrete and bolts through the web bonded the cables to the beams. Cable by cable, the stressing continued until all the ends were firmly wedged to anchor blocks. At the positions where the cables change direction, the strands pass over machined steel saddles with such a low frictional resistance that the loss of pre-stress from this cause was very slight. The secondary ropes of the main groups were anchored in the upper part of the deck, and all ends cut by oxyacetylene torch. Heavy steel stirrups were cast into the end anchor blocks of each beam. Through these stirrups, heavy rolled steel joists were threaded and given a rear support on the suspended span. With a system of wooden blocks and heavy hydraulic jacks between the cantilever span and the steel joists, the weight of the suspended span was supported. Another system of blocks was arranged between the anchor blocks of the cantilever and the suspended span. By slightly raising the jacks beneath the steel joists of the suspended span, it became possible to remove the first block between the halved joints of the anchor blocks. The pair of beams already joined by diaphragms were lowered to the next separating block by releasing the pressure on the jack. This enabled a spacing block to be removed beneath the lowering jack. By alternately removing the spacing blocks, the halved joints of the anchor blocks finally meet. To achieve a pleasing appearance, precast concrete facing slabs were attached to the outer faces of the parapet beams. These panels are made from crushed white quartzite aggregate, white sand and white cement. The aggregate is exposed on the surface, producing a light, rough, highly reflective surface which shows up to particular advantage in the usual strong sunlight and clear atmosphere in Western Australia. Above the facing panels are the cantilever footpaths. The slabs forming the cantilever footways were constructed in situ using white cement concrete. The careful design and skilled manufacture of the balustrades has contributed considerably to the distinctive appearance of the bridge as a whole. They have been made of anodized aluminium alloy, and the main sections were extruded in Australia. Specially prepared granite blocks were fashioned for curbing the bridge deck. These were placed on the line of the outside balustrading of the pathway. The safety fence for pedestrians is set back 2 feet from the roadway curb, thus separating the carriageway from the pedestrian footpaths. The balustrading posts are fixed by bolts cast into the concrete footway slabs. This is the abutment on the North River shore. The 5 30-inch diameter pipes for water and sewage, gas mains, electric and telephone cables have been turned beneath the reinforcement. The abutments are of a cellular form with a sloping slab spanning between the interior walls. The slab sloping back from the abutment wall carries the earth fill for the roadway, with a minimum fill near the face wall and the full fill at the rear. The space beneath the sloping slab accommodates the services. Concrete is delivered by crane in tipping buckets and vibrated to compaction. The carriageway, which will be finished with asphalt, will be flanked by polished granite pilasters at each end of the bridge. This is the formwork for a pilaster at the north abutment. As each group of 8 beams were tensioned and lowered by jacking to their correct level, the 18-inch gap with interlocking reinforcement was prepared for concreting. Reinforcement previously cast in the top flanges of the beam elements spans the 18-inch gap between the flanges. The useful monorail delivery skip brought the concrete along the edges of the 18-inch gaps and tipped its contents to be compacted to bring the deck to a complete unit. The 18-inch gap now being filled with concrete has set the stage for the completion of the deck. A bridge completed in a medium of construction that is of comparatively recent development. The clean shape and graceful lines were obtained by a delicate proportioning of the piers and superstructure. Attractively molded reinforced concrete pier columns combine strength with elegance, and the openings between them make for space and light, counteracting any possible tunnel effect on the underside. His Excellency, the Governor of Western Australia, Sir Charles Gardner, unveiled a plaque to commemorate the completion of the construction when he declared the bridge open. A striking and pleasing appearance fully incorporates a maximum of traffic efficiency. This is seen to advantage both on the bridge and under the bridge. The close interplay of many factors in relation to city planning, the provision of fine park-like approaches, together with what will be beautiful landscaping, combine to produce a quality of achievement. The Narrows Bridge significantly links 2 points of historic interest, Mount Eliza and the Old Mill, and heralds a new era of development in the city of Perth, Western Australia.